Hello and welcome to the new video of connection design using IDEA Statica software. In this video, we will see how to model and design the extended fin plate shear connection. We are all aware of how to design the shear connection manually and by using spreadsheets or with the formula-based software available in the market. There are various checks which needs to be satisfied in order to design this connection, and all these checks needs numerous formulations and arithmetic calculations. However, it cannot be guaranteed that the design is proper or optimized. The examination of the bolt group or the weld is a key aspect of connection design in any type of connection. There are two methods. One is elastic, which is also covered in AIC manual, and another method is inelastic analysis, also known as instantaneous center method. The elastic approach divides the loads into two components: direct shear and a moment. The direct shear is distributed evenly across all the bolts. The moment is transferred to each bolt based on its proximity to the bolt group CG. The another method, inelastic or IC approach, takes into account the bolt group's ductility uh, as well as the load distribution that occurs when the bolts begin to yield. This method is more exact, but it requires several iteration and thorough computation. When bolt forces are computed using the above two methods, it has been observed that there is nearly 10 to 12% difference in the findings of the bolt forces. The elastic method is simple but conservative. So let's put an A into all of these arduous and time-consuming calculation, and let's switch to the IDEA Statica, which employs component-based finite element analysis and design validated by full-scale laboratory test results. So the results will be as close to the actual as possible. In today's video, we will design the geometry or the design or build the geometry from scratch rather than using the ready-made templates available in IDEA Statica. The goal is to demonstrate the fundamentals of the numerous operation that must be performed while developing the connection model. So let's start. We will take this blank template. The design code will be European. The steel grade will be S275. Bolt assembly is M20 class 8.8. Concrete grid is not applicable. So let's create the model. So the first member is that main beam or supporting beam is a UB 305 165 46. So UB 305 165 46. The steel grade is automatically taken here as we set up it while making the project setup. So the first M1 is the main beam. We have to change the orientation of this member so that it can be viewed properly when we attach the secondary beams. So let's go ahead and change the geometrical type is at continuous, because sometimes we need to apply the forces at the end of this main beam, but particularly when the load equilibrium has to be satisfied. The rotation will be 90-degree. So the secondary beam will be attached here. So M2 is a secondary beam which is model, and currently it is overlapping with the main beam. So we need to rotate it by 0 and make it ended, because the secondary beam is always ended as the load is applied and transferred to the main beam from one end. So let's change the size of the secondary beam, which is 254 146 37. So Both the beams have been modeled. So you can see the secondary beam is aligning at the center line. We need to make it flush to the top flange of the main beam. So to do that, we need to change its alignment to the top flange. So you can see it is aligned properly now. The axis of the center lines are coincide with each other. So next step or the next operation we need to perform is to model the extended shear tab or fin plate, which is shown in orange color. So the first stiffener is added, but here there is a error. We have to remove this error by clicking to the related part, which is not specified. So this is a far side stiffener we do not want at this moment. So we will make it only front, and the thickness will be 12 mm, which is what we wanted, with the weld size is 8 mm. So the next step will be to extend this shear tab so that bolt will be fixed here. So to do that, we need to extend this shear tab with the offset. The offset will be 40 plus 40, 80 plus 10, 90 plus half of the web of the main beam. So edge will be the 2, which is to the right, and the value will be minus 93. So the shear tab is extended. Now we need to perform the notching operation to the top and bottom of the plate. So notch 1 will be, the A distance for the notch 1 will be 93, B will be 72, the corner is correct 1. Let's copy this notch to apply it to the top. So this is the second notch. We have to correct these values. A will be 21 and B will be 93. So we can see that the shear tab or the fin plate is correctly modeled. We need to apply it. So shear tab is model. You can see that beam is still going inside this main beam. We need to apply the cut operation so that it could be stopped here by 10 mm from the main beam. So the cut operation, everything is correct. Member to be cut, which is M2, cut by M1, which is a main beam. Cutting method is always bounding box, and the cutting plane is closer, not farther. Direction will be parallel, and the offset distance will be 93. So that it could generate a 10 mm gap. The weld, we need to remove this weld. So now with this geometry, everything is model except bolt. The bolts are three numbers of bolts, M20 class 8.8. So let's generate the bolt grid. So there is an error, we have to rectify this error. So here you can see the item count is 2, which is correct because we have to attach two items or the element. One is web of this beam and the fin plate. The item 1 will be always the web of the beam, and item 2 will be the fin plate or the stiffener, so which is correctly picked by the program. So now we have to add another two bolts, one is above and below with the spacing 60 mm. So the row will be minus 60, 0 plus 60, and the edge distance to the beam is 50, but here we want it 40, so let's make it 40. Now you can see everything is model, our connections. our connection is model, but there is one mistake. We have to shift this stiffener plate to the far side or the near side of the web. The thickness of this shear tab is 9 mm, 12 mm, sorry, and the web thickness of the beam is 6 mm. So 12 minus 6. So we have to shift this fin plate to say minus 9 mm. The axis will be x, so we have shifted in a x direction by 9 mm. So the bolts are modeled here, and our connection is fully modeled. So we can see within say less than 5 minutes we have modeled this connection. Now the next step is to apply the loads. So we have created the load case LE1. So in this load case you can see there are 3 rows. So the load is applied to the M1, which is a main beam, which we do not want. It is there because the option load equilibrium is toggled, and you can see the unbalanced forces, if any, can be see here. But since this is a simplified connection, which is a beam to beam connection, it is not necessary. So let's remove this option. It is necessary when there is a complex geometry or the number of members connecting to the one node. Then we have to satisfy the equilibrium. So in that situation, we need to make sure that all the loads at this particular joint will be in equilibrium. So let's apply the load in this connection. So we will apply the load in terms of load percentage, which is capacity, the percentage with respect to the capacity of the beam. So let's go ahead and apply 5% of axial load, which is 65 kilonewton, and the shear load will be 60 minus 67 kilonewton. So now application of the load is over. So let's calculate this connection. So the connection is failing miserably. So you can see that plates is stress to or strain is 163.6, the strain limit as against 5%. The bolt is 370 as against 100. So let's investigate what has happened. So something weird behavior it shows. So let's reduce the scale, and you can see that the beam is moving upward, which is not correct. So one main aspect in IDEA Statica is that we have to apply the load at the correct location. Here the shear load must be applied at this line, that bolt line. Currently you can see, or we can check this. You can see the load is applied exactly at the center line of the parent beam, which is not a case. The load should be applied in this line. So to correct this load application, we need to make this change, and now you can see that load is correctly applied. So this eccentric moment of 22.9 is generated in a main beam, whereas 60 kilonewton per meter moment is taken up by the beam and the bolts. So with this, we have to reanalyze this joint, and you can see the connection is passes, and yeah, it can be seen that 4.6 as against 5 and 88%, 68. This is a really optimized design which we have achieved. You can check the stresses and strain. So as you can see, the maximum strain developed at the top flange, which is denoted by this orange box, which is obvious because this is a moment will be generated due to this load. In the plates, you can see the maximum plates is 4.6. So M1 TF1, which is the main member and top flange, so this is a more stressed, and the second is stiffener. So here you can see the small part is stressed. You can check this in plastic strain. So you can see the maximum stress part. In a bolt, you can see there are some residual tension force develop in this connection, and this tension is due to the fact that there is a shear lag between this shear tab and the web of this distance between the shear tab and the center line of the beam. So these small forces are developed. You can see the shear is in a tune of 60 kilonewton, which is distributed equally, and B3 and B2 is a most stressed bolt, which is here 3 and 2. So you can see the calculation also, and the same will be printed in the report if you ask for the detailed report. So in the weld, you can see 68.7% is a weld, which is here again, and at the M1 TF1. So M1 is a main beam, and top flange weld here it is a more stressed weld. So with this, everything is all right, and let's go and change the load, and let's make it 65% shear and rerun the analysis. So you can see the plate is failed by 5.2 to 5, and the top flange is failed now. So here you can see we can add the stiffener at the opposite side of the connection, and since sometimes there may be a possibility that beam will be where this connection will be having a beam at the opposite side, and the shear connection or the fin plate shear connection of that beam will act as a stiffener. So let's add one stiffener. The stiffener is added at both the location, near side and far side, but we wanted it only at the rear side, and the thickness will be say 8 mm and the weld size will be 6 mm. So let's reanalyze this and see if our connection passes. The connection is passed with 4.7 as against 5%. But let's check whether our stiffener is correctly positioned. No, we have to shift this stiffener in the line of this shear fin plate shear tab, and to do that we need to again shift by 9 mm. So now it's okay. So the plate is the strain, maximum strain in the plate is 4.5. The plate will be a top flange and stiffeners fin plate. So let's investigate here. The most stress part is top flange, which can be easily seen here, 4.5, which is again M1 TF1. In the bolts, the 94.9, which is a B3, and you can see the shear force is almost the same. The tension force are developed in the bolts for the reason I explained you earlier. The plastic strain still is at the top flange, and the equivalent stress is like this, which is well within the limit. So our correction is optimized, fully optimized, and passes to all the checks. We can add another load case, or we can modify this by say compression force of 5%. So it is still safe. There is no problem at all for the connection. Only thing, the most stress part is now the bottom flange. So the connection is passed. Let's calculate the buckling. So the buckling multiplier is 11.37, and you can see that there are 6 mode shapes are printed by IDEA Statica. As per the code, the buckling check in the members shall be performed by limiting the by minimum limit for the buckling multiplier is 15 as per the code when it comes to the member. But for the connection components is that stiffeners or shear tab, the minimum limit is 3. So we can safely say that the buckling is not an issue here because it is near to the 15. And further, in a global structural analysis, this buckling of the members has been checked. So no need to worry about, because it is not a check, it is based on the engineering judgment. So here with this we have finished this connection design. So that's it. We have designed this connection in a most optimized way right from the scratch without using this IDEA Statica templates. Thank you for watching this video, and if you like it, please consider subscribing to this channel so that you may be notified when a new interesting video is released. Thanks again.